In the 19th century, Charles Coulomb, studying the properties of electricity experimentally, found a mathematical expression to calculate the electric force between any two electrical charges. The force between two charges, Q1 and Q2, is directly proportional to the charges and inversely proportional to the distance between them. The force is in the direction that goes from one charge to the other. F12 is the force that charge 1 exerts on charge 2. R12 is the distance from 1 to 2. K is a constant equal to 9 times 10 to the power of 9 newtons times meters squared over Coulomb squared. Remember that Coulomb is the unit of charge in the International System of Units. This mathematical expression might be familiar to you. It has similarities with Newton's universal law of gravitation, but also some important differences. In the case of gravity, the force is always attractive, as the mass is always positive. In Coulomb's law, charges can be positive or negative. This in the numerator can lead to repulsive force if both charges are of the same sign, and an attractive force if charges are of different sign. We can write the equation as where the unit vector at the end of the equation has magnitude 1 and points in the direction from 1 to 2. This constant is sometimes written as k equals to 1 over 4 pi epsilon naught, where epsilon naught is a constant called the permittivity of vacuum and is 8.85 times 10 to the minus 12 coulombs squared over Newton and meter squared. The reason for this will become clear later. To see the magnitude and relevance of the electric force, let's calculate the electric force between a proton and an electron in a hydrogen atom. Both have an electric charge of 1.602 times 10 to the negative 19 coulombs. The distance is 5.29 times 10 to the negative 11 meters. If we substitute this into the equation, we get 8.25 times 10 to the negative 8 newtons. This might seem small, but remember it is one single electron and one single proton we're talking about here. For comparison, let's calculate the gravitational force between these two particles. We use Newton's equation now, where the mass of the proton is 1.67 times 10 to the negative 27 kilograms. The mass of the electron is 9.109 times 10 to the negative 31 kilograms. This into the equation gives that the force of attraction between an electron and a proton due to gravity is 3.8 times 10 to the negative 48. This is 41 orders of magnitude smaller than the electric force of attraction. If we had 3 charges and wanted to calculate the force of 2 of them on the third one, we should use the superposition principle that states that the total force is the sum of the individual forces. So force on 3 is the sum of force of 1 on 3 plus the force of 2 on 3. Remember that forces are vectors, so we need to add vectors here. Let's solve this example with 3 forces. We will work one component at a time and then write the final force vector. So Q3, we're going to consider that it's at the origin, and the position of particle 2, it's x equals to 0, y equals to minus 4 meters, and the position of particle 1 is minus 4 meters and minus 3 meters respectively. The distance 1 to 3 is the square root of 3 squared plus 4 squared, and similarly for the distance between 2 and 3. Now the force, Coulomb's law, is written this way, and now we have to substitute first for 1, 3. That means the force that 1 is exerting on 3. And we have to project the x and the y components, so we need to project on the angle theta 1. So the cosine for the x component, the sine for the y component, and similarly, now here we have for the x component, the cosine of that angle is 3 over 5. And similarly for the y component, the sign is 4/5. Now let's go and calculate the force that 2 exerts on 3, which is vertical, so it will have no x component, only y component. And here we don't need to project because we already know it's going vertically upwards. The distance is 4 meters, so the denominator is going to be 16, which is 4 squared. And now we just group. We add all the x components together and all the y components together. That would be for x. And that would be for y. And this gives us this final force on particle 3. Of course, when there are too many charges or even a continuous distribution of charges, things get more complicated, and there are other methods to calculate the force acting on a test particle. It is worth mentioning here that for now we will restrict ourselves to the static case. That means that we will assume that the charges do not move. Of course, there are forces and there will be accelerations. These would move charges around and change the distances, and then the forces. For now, we assume everything is instantaneous and charges do not move. In a few lessons, we will talk about moving charges and the electric current. For now, may science be with you.